now. Here we go. Hi everyone, welcome to the 168th regular meeting of the New York Linux Users Group. Today we will be hearing from Paul Chiusano. Paul's talk today will be an introduction to Scala and functional programming. Paul is a senior software engineer at S&P Capital IQ and has been using Scala professionally since 2008. He's also a contributor to the open source library Scala Z and is co-writing a book with Gunnar Bjarnason, that is right? Okay, great. Functional programming in Scala. Tonight, before we get going, we have just the standard 3 requests we have here. One is please silence your cell phones. The second is please do not use the coffee machines or like phoning or anything. They make a lot of noise. And the last is be careful around the 2 tripods. We're recording and broadcasting right now, so just be careful not to jostle them as you go by. We'd like to thank Google for graciously allowing us to use this great space. We'd also like to thank our other sponsors, which are IBM, Canonical, Brandor Group, and O'Reilly Media for their continued support. In addition, NILOG would not be able to function without our many volunteers who have contributed greatly over the years. After the meeting, we encourage folks to join us for more talk and drinks at McKenna's Pub, and that's at 250 West 14th Street. It's just on 14th, a little east of 8th Avenue on the south side. That's the downtown side. We'll have a couple of groups heading over, so don't worry about taking down the address. We do have a reservation in the back, so as we arrive, the volume, the noise level will go down. We'll be able to talk. A few quick announcements. The NILOG web server is having problems right now, as anyone might have seen. We're working on repairing it. We don't have a definite ETA, but as soon as it's back up, you'll all know. Our next workshop will be on Tuesday, May 21st. Please find Rob Menez, David Bristow, or James Meldrum if you have any questions about our workshops. Does anyone have additional announcements before we get going? Brian?
Next month's talk is on MySQL forks and alternative storage engines. We have a great speaker, Ronald Bradford, who's like a MySQL ace. He's written a series of books on MySQL, so it should be a good talk.
Anybody else? All right then. If that's all of it, please join me in welcoming our speaker, Paul Chiusano.
All right, thanks everybody. Can everybody hear me okay?
A little bit louder.
A little louder? All right, how's this? A little louder still?
Move it higher, maybe.
Hello? Check, check. Good? All right. All right, well, thanks everybody for, having me come talk here. So, yeah, I'm going to be talking about Scala, Scala the language, and also sort of just functional programming in general. Functional programming is, it's a bigger topic than just any one particular language. And Scala is an excellent vehicle for functional programming, but the principles of functional programming apply, almost regardless of what language you're programming, or you can use them in any language. So just kind of as a show of hands, like, I guess how many people here are like already maybe somewhat? How many people have even heard of functional programming?
Love it.
How many people have programmed in Java? Okay, a lot of people. What about, how many people programmed in a functional language, like Clojure? Okay, so we have like, okay, cool. So yeah, I just wanted to kind of get a sense for the audience here. So I'm also, so okay, this is my Twitter handle, and I'm actually writing a book. It's called Functional Programming in Scala. I'm really just giving a very brief overview of things in this talk, and the book is like way more comprehensive than I can be, in like a 1-hour talk. And it goes a lot slower and it introduces things gradually. So if you're interested in this stuff and want to check out the book, this is the URL. And yeah, all right, so let's get started. So I'm just going to really briefly talk about what is Scala, what is the language, what's kind of the basic idea of it. And then I'm going to just sort of talk about how you can just use Scala as, some people say you can use it as a better Java, in the sense that you can do the same sort of programming that you're maybe used to doing in Java or just really in general in any sort of mainstream object-oriented programming language. So you can do that in Scala really easily. But sort of where I think Scala is a lot more powerful is that you can use it for functional programming. So I'm going to explain, okay, what is functional programming exactly? So there's a lot of maybe definitions floating around, but there's actually like a very simple definition of what is functional programming. So I'm going to talk about that. And then I'm just going to give kind of an introduction to functional programming using Scala and introducing some more features of Scala just as I go. So yeah, I'd say if anyone has questions at any time, like feel free to, you know, raise your hand or just pipe up, and you know, I'll try to just answer questions that come up. And if I can't answer it right then maybe we'll circle back at the end and answer some more questions. And yeah, so let's get going. So what is Scala? Okay, so Scala has this is a screenshot from the Scala homepage. Okay, we have this awesome you know, flip art here of the space age sun rising over the Earth there. It's a concise, elegant, type-safe programming language that integrates object-oriented and functional features. Okay, so I guess what the heck does that mean? Well, just for some background, so Scala was created at a Swiss university. The initial release was, let's see, late 2003, early 2004. It was created by this guy, Martin Odersky, who, let me see if I, Martin Odersky, okay. It was created by Martin Odersky, who, he also had some background working on generic Java, which is the effort to add generics to Java, and he worked on the Java compiler. So really familiar with Java, the JVM, and one of the big selling points of Scala is really that it's a JVM language. It's fully interoperable with Java. It's completely seamless. I'll show examples of that. And so yeah, it runs on the JVM. You can call Java code from it. And it also, I mean, in addition to being sort of a traditional object-oriented language, you can also do a lot of stuff with functional programming. So that's kind of how I would summarize what Scala is. So let's start by looking at just some really simple Scala code. So, all right, so I just want to kind of show that, so this is a very simple program, and this is, I mean, the syntax is a little bit different than Java, but a lot of the kind of basic ideas are the same. So it's like Java, it's a statically typed language. Okay, we have, let's just kind of go through this line by line. Okay, we have package declarations. The package declarations work pretty much the same as Java. I mean, one thing to notice is you're not required to put semicolons after all your statements. Scala will infer the semicolons for you. There's some, you know, finicky rules for when that happens and when it doesn't happen that I'm not really going to worry about. But for the most part, you don't need to worry about putting semicolons in unless you want to put multiple statements on one line. So when you say object and then a name, you're basically just declaring really a namespace, which is just going to have a bunch of static or standalone functions. So these functions are not associated with any class. You're not going to call them with like traditional like object-oriented dot notation. These are just standalone functions, you know, just like in Java lang math or something like that. Okay, so blocks also curly braces, same as in Java and lots of other languages. Okay, so let's look at a function definition here. So this is a little bit different than Java. So function definitions start with the keyword def, then the identifier name, and then a list of parameters. So Scala is a it's a statically typed language, so you have, so each argument to the function and all your expressions in your program have some type. So we need to say for each argument to the function what its type is. And so we say, what do we want to call the identifier, what do we want to call this parameter, and then a colon, and then what is the type? So int is the type of integers. Okay, so, and then likewise, to say what the return type is, we have a colon and then int. So absolute, it's a function that takes an int and returns an int. And so after we declare the type, we say equals and then the body of the function. Okay, we have if statements, same as in Java. It's the same syntax. You need to put the condition of the if inside parentheses. But okay, one thing that's a little different is you'll notice there's no return statement here. So we're not explicitly saying, return negative n or return n, right? We're just saying n here, and the result of the function is just going to be whatever expression is in the body of the function. So if is an expression. So this expression will evaluate to either the true branch or the false branch. Any questions about this so far? No. Yeah.
Do integers have any particular size?
There are 32-bit integers. So another thing is that, so in Java there's kind of this, oh, sorry, another question.
No, I'm okay, thank you. In BASIC, highly advanced language, you can specify in the formal parameter list whether a formal parameter is an in parameter, an out parameter, or an out in parameter. And I know they mix up the notion of reference versus et cetera of copy. Look, n appears as a formal input parameter in that thing. So is it actually changed when you run the thing or not?
No. So
Okay.
this, there's actually not even a syntax for passing in like a pointer to an int that you then modify in the body of the function. So this is just, this is an immutable reference to an integer.
Even though just it uses the same name as the input parameter and the output parameter is called n, that's just a coincidence, and your system just ignores that they happen to have the same name.
Oh, so this isn't saying, like we're not doing any reassignment to n here.
Right, okay.
We're simply saying the absolute value of n,
I understand.
if n is positive, is n.
What if it were an array?
Yeah, if we passed in like a mutable data structure like an array,
Right.
then yeah, we could mutate the data structure inside the function. And
No explicit syntax for distinguishing, but you can see what an array is.
between what?
Is there explicit syntax at the level of the formal definition of the function text? Or just somehow the variable, if the variable, say n were an array,
You'll probably answer this later in some of the examples I'm going to give.
surely true.
Okay.
Thanks.
But yeah, if you passed in an array, it would look different. I mean, we'll see examples of
I'm
working
sorry.
sequences.
You're right.
Okay.
It is a form.
Okay.
That's an array.
If you've got a more complicated function with a lot of detailed logic, and how do you tell what's the actual return value at the end?
So it's going to be, so let's look at factorial and then maybe that'll become a little more clear. So this absolute value function is just a single expression. So I didn't even bother to put curly braces around it or anything. It's just the result of the function is just the result of this expression. But we can also have sort of multi-statement definitions like this factorial function here. So again, we can have private modifiers, usual visibility modifiers as most other languages. And this is also just showing how you can write a loop. I mean, one thing to note here though is that we're not having to declare what the type of ACC is, for instance. So like in Java, you would have to say like in ACC equals 1. Scala will just figure out that, okay, ACC is an int because you've assigned it to an integer literal. This is a syntax for a while loop. I mean, it's pretty much the same as any C derivative language. And you can see we do sort of the normal operators, times equals, plus equals. And then so anytime you have a curly brace and a bunch of statements, the last expression in that block is the result of that expression. Okay.
Last statement before the curly brace.
Yep.
That's your curly brace.
Yep. Now, if this, for instance, if this were like an if, then it would be the result of the if would be the last, would be the result of the overall block. Okay, and then here's this function main, and this is an example of the syntax for accepting an array. So just like in Java, the main function receives an array of strings. It's the same in Scala. I guess so. Sort of the one difference here is that instead of saying void, you could say like public static void main in Java maybe. We just say that this returns a unit. So in Scala, there's not sort of this dichotomy between functions that are void and functions that are return values. So all functions return a value, even if that value is just a unit, which is kind of just this. I mean, there's no information inside unit. That sort of just has one. It can only be one thing, and there's no information in it, but it's still a value. So it's just a little bit more uniform. And yeah, you can see we're calling print line, and typo. I forgot to change this, but let's just imagine this said factorial instead of format apps. But okay, so this is sort of the basic syntax of Scala. One thing that's maybe different from Java that I didn't mention is that, so in Java there's sort of this separation. There's things that are primitives and things that are sort of box values or pointers to values on the heap. So in Scala, each of those concepts have the same type. We just have one integer type, int. And depending on the context of where we're using it, that will either be represented as like an actual 32-bit int just on the stack, or it will be represented as a pointer to a value on the heap. And Scala will, generally select the one that, it will try to use the one on the stack where possible. So for instance, if you looked at apps if you just looked at the class file, you would see it just took a regular primitive integer. But there's some cases where you need to sort of promote it to a box. I can talk more about that if people want to know exactly how it works. Yes?
Yes. Can you go back to the factorial example?
Okay.
So it returns int implicitly.
Oh, yes. Yes. So this is another thing. So we haven't said what the return type of factorial is, right? But Scala knows what the input type is. It knows it's an integer. And it knows that ACC is an integer because I declared it to be an integer, or set it equal to 1 up here. So based on that, it can infer the return type of the function. So yeah, if you had an if block that on one branch returned a string and the other branch returned an integer, that would actually be a type error. Yeah. So that isn't strictly true in some cases, but I'm totally not going to bother getting into it. But yeah, in general, both branches of the if have returns.
So if you have only one branch of the if, what's the statement if the expression was delivered false? So like, for example, if you get an else.
Okay, so if you have a function, if you just say if whatever, if false, whatever, print line. So this statement just has a return type of the unit. So
Yeah, but if you did basically set print line you had 5, then it would
No, so this would still have a return type. This, I mean, this is probably a bug in the program because
Yeah, but,
generally you don't want to.
so what is it gonna actually return?
So if I said val x equals that,
Yes, but what is this?
x would have type unit. So if you don't have an else branch of an if, then the if doesn't, you can't really say that the if returns a value because it may or may not return a value, so.
So,
There's another question in that.
Yes.
it would be useful if there's a function that, you know, allows you to check for type or type of kind of thing. To show that.
So I'm not sure what you're asking. Like,
So basically, you do bar equal to whatever, and then it takes, you know, shape of being an integer or something else. If you could like show us, maybe do a println or something of, you know, what the type is.
okay, so you're asking like, how do you tell Scala what you want the type to be, or?
If I wanted to check for the type of a particular variable,
Oh, okay. Yeah, so, I mean, so one thing so Scala has a interactive, this is like the REPL read eval print loop. And yeah, I can enter expressions in here, and it's going to evaluate. How legible is that?
You're running the screens.
Okay. Yeah, and so for each expression that I type in, it's printing out the result, and also it's going to tell me what the type is. So if I type print line, let's say val x is if false. Okay, anyhow, but yeah, it's equal to unit.
So unit kicks off type inference. Will whatever's receiving unit try to infer a type?
No, it's, what's that?
Task completion.
Task completion.
I mean, obviously, kind of like the same kind of instructions, right? The machine. So at the end of the completion of the task, right, it must tell code that I've done.
Yeah. Sure, so, why don't I, yeah, I guess why don't I keep going and then maybe we can circle back. Yeah, sorry, Brian.
Yeah, I was just gonna suggest, like, just go through the presentation, but one of the things when people ask questions, I can't hear what the questions are. Would it be possible if you repeated the question?
Or if you'd like, let me know, I can take my phone.
Okay, cool. Okay. Yeah, in general, every expression in Scala, it's going to return a value, and you know, including if expressions, and you know, we often use that when we're writing functions. You don't necessarily have explicit return statements. We just sort of the body of the function is just the expression that we want the function to use it to. Okay, so, and here's an example of how we actually use that module that we just wrote. So, you know, we have some other package here, we can import it. Here's just a few variations on import statements. We can import just the module sort of qualified. We can import everything in the module unqualified, or we can import even specific functions. Okay. So that's kind of the basic syntax of Scala. So we can also do like ordinary object-oriented programming. So Scala calls interfaces traits. But so we can have a trait named, which has a single function on it, name, which returns a string. And then we can say class employee, which has an ID, a first name, last name, department, and it extends name. So you always extend. There's no like implements versus extends. You just everything is extends. And then we can define this function name, which is first name plus space last name. So let me kind of point out a few things. So in Scala, the fields of the class are just going to be the arguments to the function after the name of the class. So there's no like sort of copying the fields of the constructor into the fields of the class, which is kind of tedious and boilerplate. These are going to be, all of these parameters are going to be accessible within the body of the class for any methods that you define. So there's no explicit copying. And if you, by default, in just a regular class, none of these are going to be public, none of these fields. But if you want to make any of them public, you can put a val. So here I made first name and last name public, and left department and ID private. Okay? Any questions about that?
Yeah, if you were to put name, the whole def name up in name, would employee, because it extends name, inherit that whole statement, first name plus last name? You didn't.
So I wouldn't be able to put first name plus last name in trait name because first name and last name would not be in scope.
Oh, okay. But could you give it those?
But yeah, if named also had to define first name and last name, then
So you could define an entire like interface.
yeah, I mean you could define 100 different functions on name if you really want.
Yeah,
Oh, I'm sorry, I
questions.
keep forgetting.
No, no problem. We've had a lot more questions than I think we were expecting, which is great. Just raise your hand and get called on. One of Brian or I will come over with the mic. Please just give us a moment so everyone can hear you, because it's a large room. So go ahead.
Okay. Yeah, we can keep doing questions.
What if you forget to type in extends or you don't type in extend, what will happen when you try to execute the program?
So if I
When you forget to type in extend, like.
okay, if I forgot to type that in,
Yeah. And you try
that's
to-
fine. That's not an error.
Okay.
I still defined a completely legitimate employee class. It's just not, it won't implement name. So it'll just be an employee, and if I try to pass it to a function that's expecting a name, then that would be an error. Yeah.
Can you extend multiple traits?
Just give a moment for the mic to come so everyone can hear you.
Can you extend multiple traits?
Yes. Yes, you can. So yeah, I didn't show that, but you could have 6 different traits, extend all of them. Another thing you can do, which I'm not going to talk too much about, but traits can also have default implementations of any of the functions in the trait. So that comes in handy a lot. Okay.
There's another question back there.
Oh, okay.
What do you do with overloaded constructors? If you have multiple constructors?
Mm-hmm. So yeah, if you want to have multiple constructors, the syntax for it is you define a function def this inside the body of employee, and then you have to call the other constructor, the main constructor within that. Yeah, I can show an example of that later.
You have a man with the mic over there with a question?
Oh, okay.
Yeah, so, so trait is like an abstract class, right? Which may have its own implementation.
Yeah, the way it's implemented is, it actually, it is an interface. So it will be compiled to an interface in Java. And if you have any functions that are defined, basically the Scala compiler will mix in or insert those default implementations when you extend the tree. So it's just sort of done at the compiler level.
Right. So things like overriding are still possible.
Hmm?
Like you can override, you can override a function.
Yeah.
And
So
then
you can have a
derived
default
class.
implementation in the trait, and then you can override it with something more specialized. So, okay. So I'm going to keep going because I really didn't want this talk to be about Scala. Scala is actually, it's a very powerful OO language, and a lot of people use it just for that. So yeah, nothing wrong with that. Okay, so this is just to show that the interoperability, it's completely seamless between Java and Scala. So from Java, I could call that same Scala constructor, that new employee. One thing is that name you're gonna say open paren, close paren, so it acts like a function that takes no arguments, or a method that takes no arguments. And we could do the same thing from Scala, except in Scala you don't have to put the open paren, close paren. So Scala has this, it's called the uniform access principle, which is that clients of a class really shouldn't be able to tell whether a field is derived or whether it's primitive. They should have the same syntax for accessing the field in both cases, because that just makes it easier to evolve the code. You could change a field to be a derived field later without having to update all the code that uses it. Okay, and this is also just to show that from Scala, I can import any Java classes and use them freely. So here I just imported a array, Java util array list, created a new one, and I can add to it, do all the same stuff. Basically, any Java API can call it. So yeah, Scala uses it's the same calling conventions, it's using the Java call stack. Nothing fancy there. Okay, so that concludes the discussion of sort of the basics of Scala and sort of OO Scala. I'm happy to take more questions. We can talk more about stuff maybe towards the end. But okay, so for the rest of this talk, I wanted to talk about functional programming in Scala. So what is functional programming? So functional programming, it's based on this, it's really a very radical idea. And it's based on this idea that we should construct our programs using only pure functions. And those are functions without side effects. So what is a side effect? So, okay, and so this is how we write in Scala, type of a function from A to B. So a function from A to B, a pure function, all it is doing, it is mapping values of type A, and it's going to produce a value of type B. It's not going to be doing anything off to the side in addition to that. So it's purely defining a mapping between these two things. So some things that a pure function is sort of not allowed to do is mutate variables. Because mutating things, that's something that's happening off to the side. So, okay, yeah, we can't declare x equals 1 and then later increment it by 1. Okay, we can't modify a data structure. So we can't take in an array list and then add to the array list within the body of the function. We can't set a field on an object. So we can't just set Bob's salary to 100,000. We can't throw exceptions because exceptions result in control jumping to a completely different part of your program potentially, and it's no longer just a function that's going to return a result. It's something that is going to completely change the call stack and make your program do something else. And we also, in a pure function, we can't perform I/O of any sort. We can't read a line from the console. We can't print to the screen. Okay, so at this point, you're probably thinking to yourself, well, do you write useful programs that actually do this? And that's why I said that this premise it is so radical. And so what I've said is it's not strictly true. So you can find ways to do all these things in functional programming, but you need to do them in a way that they are not observable to your programs. So that's kind of the basic idea.
Isn't it kind of like an inside-outside kind of thing? It's like whenever your side effects are in the outside world, and that's the world of iteration and in and out and so on and so forth. And when you're in functional, that's the inside world that's kind of like cut off from all of that.
Yeah, that's maybe a good way to say it. So yeah, you can sort of think of, there's sort of the world inside your program, which is pure, you're just defining these transformations, but part of your program, one of the things it can be doing is it can be creating a program which, when run, it will interact with the outside world. And
But because you have to manage state, you have to be careful about letting the outside world. Because you have to manage state, and letting the outside world in, it has to be highly controlled. Otherwise, it'll spread all over your program.
yes. Yeah, so, I mean, what I usually say is that functional programming, it's really not a restriction on what you can express. So you can write all the same programs. It's more a restriction on how it is expressed in your programs. And it's really, I mean, another way people say it is, it's really just a question of being honest about what your functions do. So if you have a function that takes an integer and returns an integer and launches the missiles, well, okay, it's okay. If you want to launch the missiles, that's okay, but you just need to have the return type reflect the fact that missile launching may be occurring. So it's really just a question of being honest about what is happening in your program and explicit. And, but at the same time, it requires being explicit about things that people aren't used to being explicit about. And like some people sort of said that, well, is functional programming the equivalent of like trying to write an entire novel just without using the letter E or something like that? And I think, maybe the first people who really tried programming in this style, they were probably, kind of weird people who were just really interested to see, oh, I wonder what's possible with this style, with these constraints. But at this point, a lot of the techniques that have kind of been worked out, and we now sort of know, okay, we know how to write very complex programs in a functional style. And I mean, at the company where I work, S&P Capital IQ, I've been doing pure functional programming there, writing lots of useful software that interacts with the real world and so forth. And I'm doing it in a pure functional style. So the benefits. So why do people do this? Is it just like intellectual exercise, like people are just doing it for fun? Well, no. So I think the big selling point is there's this huge increase in the amount of code use that you can get. And I'm going to try to give a sense of that. The other big thing is there's fewer bugs, because a lot of bugs are caused by side effects that you're sort of not aware of are happening.
Sort of like state leak.
Yeah, like just, if you sort of, it's actually a really interesting exercise to, every time you find a bug, like do like a bug log and just try to record, okay, what actually led to this bug occurring? And I would say like 90% of the time, it's due to some sort of state bugs. Another thing is that functional code is really easy to parallelize. I'm not going to talk too much about that today, but you don't have any of these stateful interactions that you have to worry about. You kind of just run two pure computations in parallel, and you know that they're not going to interact with each other. It's also very easy to test functional code. You just need to, provide the inputs to the function, get the output, and make sure it's what you expect. And I guess the other thing, so some people say that functional code is more complex, more complicated, and maybe in some ways that's true, but I would say functional code is extremely transparent. When you look at a pure function, the only thing that you really need to understand, or the only thing you need to do to understand that function is just really look at its definition. You don't need to think, oh, well, what hidden state has been sort of set up or initialized behind the scenes that is going to affect what this function does. You just sort of look at the function and look at the other functions that it calls, and you can just sort of trace through what it's going to do.
Would it also be fair to say that, in a sense, with functional programming, you can control time better?
Could you repeat the question?
I'm not sure what you mean by that.
Well, in a sense that, with regard to state is something that happens throughout time, and a value you have recorded in state. Let's say you have state, and you have a value recorded in memory address X. Over time, memory address X changes its state as you run the program forward. And in imperative programming, you set up breakpoints to catch what's in that location as you're going forward. In functional programming, it's immutable. So you can run the program forwards or backwards. That state's never changing. So you have complete control over time in a way that you don't have in imperative programming.
Yeah, I think that's fair. Yeah, exactly. I mean, any sort of propagation of information is very explicit in the program. Yeah, variables aren't just sort of mutating, being modified out from the root. Yeah, so that's one way to look at it. Okay, so what I wanted to sort of spend the rest of the talk going over is just really just introducing, like, well, what is functional programming like? What do you typically do when you're functional programming? So I'm going to go through these like very sort of simple examples that I'm really just trying to capture sort of a little bit of the essence of what it's like to sort of think functionally. And it's very hard to like come up with these like super complex, compelling examples you can cover in a 1 hour period, but I'm just hoping that this sort of gives the gist of things. So here's a function that I wrote to sum up a stream of integers. So stream is a immutable, lazy sequence of integers. Stream. So as we inspect the stream, we're going to be possibly computing the remaining values. So we could actually have an infinite stream that so I can actually say stream.from. This actually represents the infinite stream of integers 1, 2, 3, 4, 5, all the way up to infinity. But it's not actually fully computed yet. So I can say take 20. So I can say take 20 to list, and I can get the first 20. But I can put anything in here. I could say 200 or a million. So okay, so a stream, one way to think of it is it's a first-class loop. You might think of it. And so this is a stream of integers, and we have a current accumulated total. This is an example of a default argument in Scala. So I can actually call sum with either one argument, in which case ACC will be 0, or I can call it with 2 arguments, in which case that will be value. And you can see this logic is pretty simple. So if the stream is empty, then I just return the current accumulated total. Otherwise, we return we're just going to recurse. So we're going to say, okay, add to the current total, whatever the head of the list is. So head is, so you can see res3.head here. So if I have, so okay, head is just the first element of the list, and tail is everything except the first element. Yes?
Can you stream other things than ints? I'm assuming you can since there's
yeah.
a type there, but how would you stream a float?
Yeah, so I could say,
Would you have to give it like a step value for floats?
Yeah, there's a lot of different functions for creating streams, but yeah, you can have a stream of anything.
A stream, like,
Stream of strings, ints, doubles, floats, employees, anything.
And it's lazily evaluated.
and, I mean, how do you have a stream of arrays? Or a stream of lists, or a stream of objects, unless that object already has a does the object need like a way to deal with the stream?
Some kind of generator?
Yeah, you would have some I mean, you probably wouldn't get the stream by like literally typing it in, literal, but you'd have some process that generates arrays, and then you could create a stream from that process.
Could you, I mean, can you type string into the REPL, and what do you even get? Like what is a?
I mean, I can say hi there.
I think he's asking about the automatic generation.
Oh,
of
how do I
context.
generate it?
Yeah. I
yeah,
don't think
there-
for all types you're going to have a generator.
Alright, so for ints, there's an automatic generator starts at 0. Good.
Yeah, so the from function, that's just like a convenience one that happens to exist. There's maybe later I can show,
Okay.
but there's a whole bunch of ways you can create streams. Yeah, like a very common thing is like you have some sort of initial state and then some sort of step function that you're going to use to progressively transform that state.
There's like an implicit toString that's being resolved, right?
Oh yeah, that's just in the REPL here.
Right.
Yeah, whenever I evaluate something, it's going to print out, it's going to call toString on it to print it out.
Does Scala do recursion optimization?
Yes, so I was actually just going to talk about that. So this is an example. So this is a recursive definition, but so ordinarily, if this were just evaluated kind of naively, this would blow the Java call stack if you had a large enough stream of elements. But since this is in tail position, so we're not doing anything after the recursive call, Scala will actually compile this just to the same sort of code as if you wrote a lot of same sort of byte code. Okay, so this is the sum function. So, oh yeah, and then I just showed this. So one thing you notice, this happens all the time when you're programming, is you often notice duplication. So I might write the sum function, and then sometime later, I might write the product function. And you can see the definitions are very similar here. Okay, this is operating on doubles. Those are 64-bit, double precision, floating point values. But I mean, the definitions, the structure is very similar, except I have a typo. I call sum again. But okay, pretend that's product. Yeah, you can see we're doing the same thing. The only difference is that the accumulated value, it starts at 1 for product.
So the return type should be.
Return type should also be double. Okay, so that should be double as well.
Traditionally, when you have other example of functions, you have two arguments to the function. One is access string double, and one is double divided 1. When you call the other one, there was a list of numbers separated by commas, and I was wondering how do you, can you initialize the ACC or the imply any rate? How it has not part of the argument when you called it before. So I was expecting some to be parentheses, some list, and some net value would be assigned to ACC, and it wasn't just a bunch of numbers or a stream. So how
Is the question around the use of recursion and how recursion generates the list that gets returned?
No, I'm saying that when you called sum, there was, I would expect the XS and the ACC as part of the arguments to the function, but it was only just a list of numbers. So that means somehow ACC was.
I wasn't calling sum here. I was just calling stream. So this is just some convenient syntax for creating a literal.
Oh yeah, I saw the stream, but I didn't. I thought you showed how sum was called.
Oh no, I haven't shown. Okay, so I'm sorry about the typos here, but okay, so sum and product very similar in structure. So Now, these are like very short examples, so, you know, it probably doesn't matter if you just re-implement these to, you know, both using explicit recursion. But if you want, we can factor out the common structure here. So let's think about what we have to do. So we're going to need a function parameter for what to use as the sort of initial ACC, right? So we're going to need a function parameter for that. And we're also going to need a function parameter for this function. And this function, so here it's plus, it's the plus function. And it's taking two arguments, the current accumulated value and the current value of the list from the string. So we're going to actually need to parameterize our definition on a function. And this is something, so this is called a higher order function. This is something that's done all the time in functional programming. So let's look at kind of how this works. So we're defining this function fold. So fold still takes a string, but notice that we don't actually care what the type of the string is anymore. The only thing that we care about is that, okay, the type of the string, A, whatever A is, maybe it's int, maybe it's double, has to match the type of the accumulated value, A. And the function that we're going to use to sort of combine successive elements of the string also needs to operate on A's, whatever A is. And you can see the structure of the code is almost the same as sum. X is empty. We still return ACC, so that is actually syntactically identical. And then otherwise, instead of calling sum, we're calling fold. And then we're just calling the function that we were passed in to update the accumulated value. And then we're just passing the function along. Okay, so does that make sense? Cool. So using this, we can now define sum in terms of fold. So we say fold, x's, ACC, and then we're passing it, essentially we're passing it the plus function. And then we can also do the same thing for product, except we're going to pass it the multiplication function. Okay. So it's kind of a sidebar. So what we did in this, at the bottom here, is we're actually, this is called a function literal or an anonymous function or sometimes a lambda function. Oh, sorry, yeah.
In that last one, what is y and where does it come from?
So yeah, I'm about to explain. Okay, so yeah, all right. So a lot of times when you're doing functional programming, you write these higher order functions a lot, and you don't want to always have to give them a name. So I might have a plus function that happens to be laying around, and then I could actually pass that to fold. But in a lot of cases, you may not have a function that's named that's already lying around, and you just want to quickly just inline create a new function right there. And so Scala has a very convenient syntax for doing that. So here's just some examples of this. So this is a function that takes one parameter, x, and it's going to return x plus 1. You can also annotate the type if Scala is not able to infer what the type of the parameter is. You can say, okay, x is an int. Here's some other syntax. If I need to take two parameters, an x and a y, and of course you could call these anything you want. You just comma separate them. You could have a function that's a block, so you could have a whole bunch of statements in there if you wanted. And then there's even some like more shorthand syntax. You can actually just say underscore, underscore plus underscore, and that will be a function that takes two arguments and adds them together. This comes in handy for if you need to reference a method of a class and pass that as a function. like our employee class that we wrote earlier. You could say underscore dot department and pass that as a function. And that's going to be a function that will pull out the department. Okay, so one thing I notice about this, so this example, hopefully that makes sense, but one thing you notice is that actually if you look at the definition, it doesn't really care that the return type is the same as the elements of the string. So, I mean, this pattern here is a very general pattern. And if I wanted to do this to say count the number of employees in the sales department, I mean, conceptually it's the same sort of thing in that, I'd want my result type to be an integer, the count, but my A is going to be employee. So I have two different types that I want to use this at. And actually, if you sort of just look at the function, it turns out it's even more general than the type that we gave it. So we can actually generalize this a little bit further into this function fold. So now the accumulated value can be a completely different type than the elements of the string. And the function just has to take the current accumulated value and the current value of the list and return a new accumulated value. And we can still use this exact same function for defining the sum and product, but we can also use it for lots of other things. So yeah, here's an example of using it to count up the number of employees in the sales department.
Can you go back to the previous slide for a second? Okay. Immediately after.
Keyboard just got stuck or something. But yeah.
Immediately after the fold statement, you had the type parameters in square brackets, basically denoting the input types that fold takes, right?
Yes.
But you only specified two parameters. You specified A and B. You didn't actually specify the third argument, which is the function. I guess my question is what would be the type of the function if you included it in the type signature in the brackets?
So
the next slide, A and B.
Next slide.
Yeah.
That's it.
Which one?
There's the one that had both A and B in brackets. Right there.
This one
yes.
here.
Yes.
Okay.
Okay. So
Okay.
fold actually takes three arguments, and A and B are the types of the first two arguments, right? What would be if you wanted to include the type of the function in the bracketed expression? What would the type of the function be?
Oh, so the function. So okay. So the square brackets are
That's
just
type signature, right?
So the square brackets. So after fold, so A and B, you're just introducing type variables. They're not. So they're type variables that you can then reference in the rest of the signature. So I'm introducing a type variable A, a type variable B. What's that? Yeah, they're just, yeah, they're, and I can then reference those parameters elsewhere in the signature. So
It's like generics?
Yeah, it's generic. This is the syntax for generic. So like that, the stream that I get has to be of type A, and then the function, its second argument also needs to be of type A. So by referencing the same symbol in multiple places in the...
So it's just a collection of types you're going to use in the type signature?
Yes.
Okay.
Can you specify any constraints on can be, for example, the able method text?
Yes, you can.
Can what?
Yeah, I'm not going to show that here.
Please.
Oh, so the question is, can we specify constraints on A, like that A is named or something like that? I mean, you could just say, yeah, I guess the answer is yes, you can do that. I mean, you could just accept a name as the argument type. You could also accept an A that is a subtype of name. So you have a lot of flexibility. I guess I'm probably going to punt on that. But yeah, you can.
On the previous slide, you had underscore department. Does this really looks awfully similar to duck typing? Does this imply that Scala supports it, or how does this generally works? Because you don't know the type of underscore that too.
Oh, so Scala will only let you use this in a context where it knows that this is an employee. So this isn't, yeah, this isn't like a structural or duck typing thing. It's gonna just, as long as it has a name, a method named that, it's gonna work. Okay. All right, so let me keep going here. So, okay, so one thing I just sort of noticed about looking at this definition of counting the number of employees in the sales department is that this loop here is actually really doing two things. So on the one hand, we're taking each employee and we're kind of mapping it, or we're converting it to either a 1 or a 0. And then, so that's sort of one operation. And then the other operation is, okay, now that we've converted each employee to either a 1 or a 0, we're then just summing up that sequence. And you might not think of it, you might not think of the problem in that way. Like most likely if you were doing this as like a while loop, you'd probably just write one big monolithic loop that kind of did everything. But you know, for more complex programs, it's nice to be able to assemble your loops by sort of sticking together different pieces. So if we wanted, we could actually separate this out into two separate functions. So one that is going to simply just apply a function to each element of the list. And then another function which is going to sum them up, which is the one we already wrote. So that function already exists. It's called map. And map, so here's an example of its use. So map just applies a function to each element. So map applies a function to each element of a sequence. So here we're just saying, you know, E is going to be of type employee. We're just saying it's Department of Sales, map it to a 1, otherwise to a 0, and then we're calling sum on that. And the nice thing about working with streams is that map is actually lazy. So map is not going to, you can call map on an infinite stream of values. And it's only going to compute the mapping sort of as you expect the stream. So this is sort of, when you actually execute it, it's going to be roughly equivalent to if you just wrote one big monolithic loop. But it's going to sort of, you're sort of assembling that loop from two different pieces. And so that sort of thing happens a lot, just like looking at code, noticing duplication, factoring things out by passing in functions. And just by doing that, you discover, lots of different, lots of different kind of abstractions and useful functions that way. This is an example of, this is how map is actually defined on the Scala stream type. So this is an example of pattern matching. So we're saying, okay, if the stream is empty, then, okay, return the empty stream. And if the stream has a head and a tail, a first element and a remaining elements, then apply the function to the head, and then map over the tail. So, and this funny operation here is the construct a new stream from a head and a tail. And so one thing that's like really interesting about this sort of definition is it's in a way it's sort of inevitable. Just by defining this signature, map parameters on a type B, a function from A to B, and it needs to return a stream of B's. There's really only one definition that is going to satisfy the type checker. So in this case here, I have to return a stream of B's, and H is going to be of type A. And there's really only one thing that I can do at this point, which is to apply the function that I have to produce the output. So a lot of times functional programming, you sort of define what type you want your function to have, and then you just sort of follow the types to the implementation, and things just sort of snap together.
So how does the pattern matching on a street construction actually work?
How does it work?
Yeah, so how does, for example, the example right there, the pattern match H, history operator T, how does H get assigned type A?
So, I mean, it's just part of the Scala compiler. I guess internally it's going to be, it's going to compile to like some if checks, like, okay, if, it's going to inspect the stream and then do some stuff. If the stream's empty, it's going to go to that one branch. If the stream is not empty, it's going to then introduce into scope two variables H and T, which you can then reference. So it's kind of just compiling to something that you could, in theory, write with some if statements or some nested if statements. But it ends up being kind of a lot more declarative and less finicky to get right. But yeah, I don't know if that answers your question. Okay. All right. Well, maybe come talk to me after. I could definitely say more about that. So I have a lot more stuff. We've had so many questions. I'm trying to decide, which is actually really good. I'm glad people are asking questions. So maybe I'll go through just one or two other things and then kind of wrap up, and then we can do some more questions. But yeah, so another example of a function that kind of comes out of this process of just like looking at code, noticing duplication, factoring things out. It's this function filter, which is going to take a function from A to Boolean, and it's going to remove any elements from the string that don't match that function. So this is another way of writing that same program is, okay, we're calling filter and only including things that are in the sales department, and then we're calling the length function on the resulting string. And that's another way of counting the number of employees in the sales department. And here's how it's, but here's the definition of it. Very similar type of thing using pattern matching. We're saying, okay, if the predicate matches, then okay, include it in the output. Otherwise, don't include the first element in the output and just the first filter. Yeah, and so these functions that I just sort of introduced here, these aren't really, they definitely come up a lot and they're very handy, but they're not in any way unique. And if you just go through this process of kind of factoring code and looking for these patterns, you notice lots of other operations. So here I just kind of made up an example of sort of another pipeline that you might write in Scala. So this is doing a whole bunch of different things. But you can see, it's this very declarative thing. Okay, this is hypothetical. We're taking stock quotes and trying to match buyers and sellers or something. But yeah, we can sort of string these transformations together. We can also zip. That's another operation of just sort of taking two streams and pairing each element, pairing corresponding elements together for further processing. And so this is just an example of the sort of thing that maybe comes up as you sort of build up a little library of functions like this. And yeah, if you look at, let's see. So this is the actual Scala string class. And I mean, there's a ton of different functions here, and these are all, I mean, most of these functions are not, they're not really specific to any domain, they're just encapsulating some pattern, a lot of them, that comes up a lot across lots of different domains. So filter, find, there's fold, fold left, fold right, you know, all these different variations. And they come in really handy in lots of different cases. Okay, so that is sort of, you know, I think that maybe gives sort of a feel for what it's like to kind of do functional programming and discover and factor out these patterns. I was going to go through another example in a completely different domain of error handling, but I think I'm probably going to table that. Just
let me suggest, if you feel like it would be lame, why don't you go ahead? I don't think you're under like a real time constraint, so why don't you go ahead? We'll just hold questions until later on.
Okay, yeah. All right, okay.
Thanks.
Unless, of course, you're done.
No, I can keep going. I just, you know. Okay, yeah, so I'll keep going. So this is a completely different domain, error handling. So let me just give an example here. So here's this is actually another bit of Scala syntax. This is a map literal, so you can, there's a nice convenient syntax for creating maps in Scala. So this is creating a map from strings to integers. And if I have a map like this, and I look up some key that's not there, D, so what should I get back? So, I mean, different languages and libraries make different decisions about what to do here. So, I mean, one option is, okay, I can throw an exception, key not found, that's like what Python does. I could return null, that's what Java does. You know, like undefined. Yeah, null or undefined, so some sort of value like that. But kind of the problem with, you know, the problem with each of those approaches is it kind of can generate a lot of boilerplate whenever you go to use a map. So if every time you have to look up a key in the map, you have to worry about catching an exception. That can generate a lot of annoying code of, you know, if you have to look things up in two different maps, you need to look it up in one, and then maybe catch the exception and look it up in the other. Same deal if you return null, you have to look it up and then check to see if it was null. If it is, then maybe continue. So this is just sort of something that comes up a lot. And so the approach that we're going to use in functional programming is we're actually going to return a value to represent that can be present or absent. So it's this type option. And it can have one of two different cases. So these are really just subclasses of option, or that's how they're represented in Scala. But when we say that they're a case class like this, Scala does a few different things for us. So one is it'll actually generate like hash and equals, so I can use them as keys in dictionaries and so forth. They get a nice two-string function generated for us automatically. But that's actually not so important. What is important though is that we can now use these as patterns in a pattern matching expression. And so this is what we're actually going to return when we look something up in a map. So we're not going to return null, we're not going to throw an exception, we're going to return an optional result. Okay? So here's an example of just using option and just sort of using it directly. Okay, same employee class. This time I made it a case class, so all these fields are public by default in a case class. You don't have to say val in front of each field like in a case class. So case classes, they're also just really handy for creating, you know, little structs or just a container of data that you don't necessarily have any methods or functions associated with. It's just something you want to be able to pass around. And So here's an example of, I have two different department maps, and I want to get Alice's salary by looking up in both maps, and whichever one the employee whose name is Alice is in, I want to use that salary. So you can see this is the code to just sort of do that directly, and this is actually not that different than if you were to do the same thing in Java and check for null after each map lookup. So we say, okay, check in the first department. Okay, if it's not defined, then check the second department, and then once we have an employee, we're going to check, or an optional employee, we're going to check, okay, is it defined? If no, okay, just return 0, otherwise return that employee's salary. So this is just another example of, okay, we've defined some data, defined a data type, we've started using it, and we're noticing some sort of boring, repetitive code that we have to write when we're working with it. So if you sort of look at, let's look at this first block here. I mean, what are you really specifying? I mean, what is ideally the information that you would like to specify? I mean, ideally, I would just like to say that I want to do a lookup in this first map, and then if that fails, look in the second map. All this pattern matching, that I have to do here, that sort of feels orthogonal to what I'm trying to do. Same deal here. I have an optional employee, and I either want to, if I do have an employee, I want to pull out the salary, and then if I don't have an employee, I want to just return 0. So this is another example of looking at this code, you can sort of take the pattern that you see in this code and factor it into more general functions that you can reuse in other contexts. So that operation of having a computation and then that returns option, and then you want to fall back to another computation that also returns option. There's a function on option called or else. So if I write if I say sum 1 or else sum 2, it's going to return the first one because the first one is defined. But if I say none or else sum 2, then it's going to return the second one. And moreover, this funny arrow here is actually indicating that this argument is lazy. So this actually won't be evaluated unless the first one is undefined. So you can sort of do that second map lookup, and it won't actually be evaluated unless the first map lookup fails. And then there's a whole bunch of other functions on option that you can use as well. So here's an example of get or else. So this takes an option and converts it, pulls out an A if that A is defined, and if not, it uses the default value that we provided. So I can say none.get or else I, but I could also say sum I get or else. Doesn't really matter what I put because this won't be used because the value is defined. So these patterns, we can also define map, which is applying function to the option if it's defined. Filter, so, and these are just functions that just come up if you just look at the use cases of option and how you notice the patterns that are emerging. So here's like an example of that same code written now using these helper functions on option. So we can say department get Alice or else department 2 get Alice. Then we can call map, pull out Alice's salary, assuming we've gotten an employee from one of those two departments. And then finally, get or else 0. And this, I think, is a lot nicer. I mean, it's more declarative, and I think once you understand the meaning of these functions, it's actually easier to understand what it's doing versus having to go back to the explicit pattern matching, where you really have to follow every line of code to understand what it's doing. So, so that's just like another example of a domain. And what's interesting is that, I mean, you notice like a lot of operations come up in different domains. So for instance, that operation math came up in this domain as well as in the domain of operating for sequences. Same with filter. And so as you sort of go through this, exercise, you notice that, yeah, all these domains, which actually seem like they're very different, maybe at first, oftentimes share a lot of common structure, common pattern. And you can actually even abstract over those patterns and reuse code across all these different domains. So you can actually write algorithms sort of once and for all, and capture these patterns once and for all, and not have to keep repeating them in all these different domains. And so yeah, so I think that's kind of where I was going to stop. So I'm like almost done like wrapping up, and then we can do questions. But yeah, so that I'm hoping that kind of gives a feel for what functional programming is sort of like. But yeah, I mean, functional programmers, they've been at this for a while, and they've just by going through this process, have discovered a lot of different abstractions and a lot of different patterns, and given them names and so forth. And yeah, so there's a lot to it. It's like a very deep subject, a lot of things that come up. But it's very natural in the sense that it just sort of emerges from looking at code, factoring out patterns, and just sort of repeating that. And you end up discovering a lot of these different things. So yeah, so we can do questions. Yeah, it's scalaline.org. That's the homepage for Scala. And then the book, which I think does a way better job than I've done in this talk, it's kind of introducing these things. Functional programming in Scala. It really just starts from like the absolute basics. There's a lot of exercises to go with the concepts, so you can really like teach yourself. There's exercises, answers, hints, all that, so you can work through the book. And yeah, this is the homepage if you want to check it out. And actually, so the book is not in print yet, but 14 and 15 chapters are already available online, and you can pre-order the book and get access to those chapters right now. So I wish I had like actual hard copies of the book to get out. So yeah, we can do more questions.
So when you combine Scala with Java, for example, right, which does throw exceptions. In functional programming, how do you handle the exceptions that are thrown from Java when you're calling Java library?
Okay, yeah. So if you're working with a Java library that throws exceptions, I mean, you can catch exceptions in Scala. I mean, I can show the syntax.
Also, there's the same try catch.
Yeah, so I can say throw new, exception. The syntax is a little different. Yeah, it's basically try expression and then catch. And you can say like case E IO exception. Oh, so it's, you're just naming the exception. Just like you said, catch IO exception E, like Java.
So you wouldn't have to explicitly in your function definition say throw if you want to.
Oh yeah. So yeah, Scala doesn't have like checked exceptions. You can, if you're interacting with like a library that yeah is expecting a function that needs to have a checked exception, you can. There's a way you can say in Scala, oh, this function will throw that exception. But Scala, so unlike Java, Scala will not enforce. It won't force you to catch an exception.
And if you don't have to catch it, it will just pop up.
Yeah, so, and if you don't catch it, yeah, it works perfectly.
This seems like it's designed for parallelism. You don't want to have any state, so you don't have to have blocks and return threads. Is that sort of the way that they're using it?
Yeah, I mean, it's functional code. Yeah, it's very easy to parallelize because there's no shared state that's being modified. Each computation is basically independent, and if you want to evaluate two computations that are independent, you can do so parallel. So, I mean, and there's even some like fancy features. Like, okay, if I have a list, I can actually create a parallel list by just saying .par, and then if I say map, +1, that will actually perform the mapping in parallel over each element of the list. So here it's kind of a dumb example because increment integer takes no time, but yeah, I mean, this is just to show like how easy it is. And this is just one example of an API for doing parallelism. And there's lots of other sort of APIs that you can build, but the point is that it's very easy to do. There's really no restrictions on doing it because we know that there's no interaction between any of the sort of subtasks for each element.
Two things. If you can tell us how you do testing and debugging any differently in a functional language. And also, I'd love to see some best practices similar to design patterns for functional style programming. I'd be the first to line up for your book. Great.
Well, so okay, so testing, I mean, you can do testing in pretty much the same way as, I mean, you can even use JUnit if you wanted. There's a really nice library called Scala check, which yeah, there's another sort of style. Oh, my connect is there. Okay, well, yeah, but there's a really nice style library. This is just another example of a domain where you can kind of discover these various patterns. But in the library Scala check, you would actually, so a pure function is very easy to test. So you have some, all you really need to do is be able to generate or specify what its inputs are. And you have some function or some property that you want to hold for the output, right? So a sort, if you wrote a sort function, you're expecting that, okay, when you give it a list, the output should be sort. And it's very easy to say like what it means for a list to be sorted.
Fluent programming. That's what they call it in JavaScript. Oh well.
Okay. Okay. I'm not familiar with that term, but
okay.
But yeah, so there's some really nice testing libraries that you can build. And then as far as, so for your other question, design patterns, I would say the book does like a way better job of building up. So I guess the organization of the book is that it kind of starts out by just, introducing Scala, introducing the basics, and sort of what we do is essentially discover the patterns of functional programming kind of as we go. And you end up discovering, yeah, I guess you could call it I mean, some people call them design patterns. I think, I just call them, they're just common structures or just things that recur over and over again. And they're sort of different than the sort of OO notion of design patterns, but yeah, definitely there are, you know, very common patterns that emerge in all these different domains.
So, one or two more questions. I think we have a question over here.
I have a couple questions. Going back to the map that you had, is the shape option supplied to the libraries, or is it something that you define out?
Oh, that's...
And what happens if you don't define it out?
Yeah.
You try to access a key from a map, and that's not defined.
Yeah, option is part of the Scala standard library. It's, yeah, here it is.
The second question that I have is it possible that you could parameterize all the functions, or only the functions that you try to abstract out that you could parameterize? For example, the sum and product, right? You fold it into a function, and that's parameterized. As a standalone, could I parameterize the sum and load, and then I could pass integers or doubles on that?
Oh, I see what you're asking. So you want to be able to use sum for both integers and doubles. Yeah, so yeah, I guess the way that you would do that is by passing as an argument a function that says how to add. So it's, you can parameterize over a type in which you know how to do addition, subtraction, multiplication. And so if you actually look at, let's actually look at some here. Okay. So, okay, this signature is somewhat scary, but yeah, and this uses implicits, which I didn't talk about, but you can sum up any stream or list for which you have an instance of numeric, for which that thing is numeric. And it's implicit, so you don't actually need to explicitly pass that argument, but you know, the usual things are numeric, so integers, doubles. You can also define your own numeric classes, and that will work with the sum syntax. Like, yes, yeah, it's the same idea as type classes.
But let's see the next one. We point 0 after each of the numbers.
Okay.
Just wanted to make sure.
Questions?
Yeah, sure.
All right. So at the end of every meeting, we have some giveaways. So I'm sorry, we're going to wrap the questions. Anyone who wants to ask further, please, Paul's going to be at the bar afterwards, so just come and join us. And so what we have here is we have 5 questions. I hope you're all paying attention. 5 questions that Paul's going to ask, and whoever gets the right answer, and I'll try to be as fair as I can. And it's a big room, I'll try to get everyone. But there are 3 ebook vouchers and 2 copies of 7 languages in 7 weeks. Scala is one of the included languages. So by all means, if you win, you can choose whichever one of these you prefer. So go for it.
So I'm sorry, how many questions should I do here?
We have 5 giveaways, but you can ask as many questions as you want.
And then you can fold over.
You guys are going to be here for a while.
Show of hands, not
All right, so first question is, Scala was initially released in what year?
2002.
Wait, okay, sorry first, but the thing is, make sure you raise your hand and don't call out answers, because I'm going to go for whoever raises their hand. I don't want anyone walking out upset about this, please.
It's late 2003 and early 2004.
All right, so come take your bid.
All right, next question is, who is the creator of Scala?
I saw him before we get this.
Mark Oderski.
Yes.
All right.
Okay, next question. What is the basic premise of a functional program?
Hold on, no calling out, no calling out. I can't.
This is lazy evaluation of answers.
Function composition.
Function composition. I'm sorry.
All right, let's try again. Show of hands. Let me go over here.
Okay. Everything should be functions with no side effects.
Yes.
All right, there you go.
You have to be careful, the party line's gonna change now.
Okay.
Everyone, Jay's having a party, so he'll tell you where it is.
Okay, next question. Let's see. What is the name for the operation that applies a function to each element?
I didn't do that with everyone right here.
Map. Yeah. All right. So, okay. Next question is, what is the now? I was gonna say it was right type, but we have like. All right. So yeah. Okay. So I'm gonna ask. What, write the type of a function that accepts a string and an integer as arguments and returns an integer. So if you raise your hand, you're just going to come up and type it in.
Oh, this is new. We've never done this before. Does anyone want to try this? Okay, come on up. Oh, it's the first person I see. That's the hard part. It's such a big room.
A function that accepts a string and an integer.
I'm sorry about that.
Yep, that's right.
All right, so that's a voucher for you. All right, so we're out of vouchers or anything, but if anyone wants one more question, we all right, so we're done. All right, thanks everyone. We're going to be taking thank you, Paul. We're going to be heading over to the bar, again, McKenna's 250 West 14th Street. We'll be gathering and kind of walking out in groups. So you have to go on your own or go in groups.